Hi everyone, welcome to the next of the A-level physics revision videos that I'm putting together for you. The topic of this one is going to be looking into stable and unstable nuclei, and one of the things that dictates whether the nucleus itself is stable are the forces between the nucleons within the nucleus. And there's two main forces in play, and they are the Coulomb force and the strong nuclear force. I'm going to talk about each of them individually, and then we'll talk about how that leads to the nuclear stability. So first of all, the Coulomb force is the force between charged particles, and in the nucleus, the charged particles are the protons. And from GCSE science, you should know and you should be happy with the idea that if I try and put two positive charges together, or even two negative charges together, they're going to exert a repulsive force on each other. And that's what's happening between the protons within the nucleus. Okay, very short range, the forces between the protons are very, very big. And that gradually tails off and it follows an inverse square law, getting smaller and smaller and smaller. As distance doubles, that force goes down by a factor of 4, but it never actually reaches 0 because it's a very long range force. Okay, there will always be a residual of that Coulomb force regardless of distance. So the Coulomb force there, just put a couple of notes, repulsive, between like charges. They are long range, and it follows an inverse square law. So within the nucleus itself, that Coulomb force is trying to push all of the protons apart. So there's got to be something else in play which is able to keep it together. And that's where the strong nuclear force comes in. And the strong nuclear force is represented by this green line here. But you can see that there is a component of it which can be repulsive, and it is repulsive above 0.5 femtometers, or 0.5 times 10 to the minus 16 meters. Okay, and as we go closer to 1 times 10 to the minus 16 meters, that force becomes very strongly attractive. But as we move up towards 3 times 10 to the minus 16 meters, that force is virtually 0. So it's a very, very short range force. So I'll just put a couple of notes here that strong nuclear force is repulsive above 0.5 times 10 to the minus 16 meters. It's strongly attractive at around 1.0 times 10 to the minus 16 meters, and it is 0 but greater than 3.0 times 10 to the minus 16 meters. Okay, but at a particular point, what we need to happen is for the Coulomb force, the repulsive Coulomb force, to be equal with that attractive force which is provided by the strong nuclear force. And that happens at around about this distance here. If I draw that line there, we can see that roughly speaking, the Coulomb force is equal, it should come to about here, the Coulomb force is about equal to the strong nuclear force. Okay, and that is in equilibrium at about 0.7 times 10 to the minus 16 meters. So what that means is that the Coulomb force and the strong nuclear force are balanced. Okay, we talked about balanced forces quite a lot at GCSE. These forces here are balanced, and when they are balanced, that just means that nucleus is going to be stable and it's not going to experience any alpha decay, beta decay, and so on like that. Okay, so this graph is something that you need to be familiar with. You need to be able to explain the features of. You need to be able to talk about, in particular, the distances and the directions and magnitudes of the forces which are involved. So, as I said, these key points here are definitely something you need to take away and you need to remember for your exam. in describing the nature of the strong nuclear interaction and its relationship between the Coulomb force. Okay, I hope that helps you. Thanks for watching.